morning. I'll be starting with the introduction. Humans have long dreamed of space and gaze up at the night sky. The development of rockets in the second half of the 20th century have opened the door for space exploration due to their strong ability to violate gravity and meet orbital velocity. Sputnik 1, the very first artificial satellite, was launched into space by the Soviet Union on 4th October 1957. Russian left Yuri Gagarin orbited the Earth in Vostok 1 on 12 April 1961, making him the first human to do so. During his 108-minute flight, he reached a height of 327 kilometers. Astronaut Neil Armstrong made one tremendous breakthrough for humanity as he set foot on the moon on 20th July 1969. Between 1969 and 1972, 6 Apollo missions was created to investigate the moon. Unmanned spacecraft quested and took photographs of the moon in the 1960s before any astronaut set foot on it. All these space missions have made a significant breakthrough in human space exploration. However, there are also many cases of failed space missions that caused devastating financial loss. The most significant incident was on 28th January 1986. The Space Shuttle Challenger exploded after the takeoff in 73 seconds. Chris McAuliffe, a New Hampshire teacher who would have been the first civilian in space, was among the 7 crew members who died. We can see that a failed space mission could also result in a serious accident with loss of life. Besides that, it may also cause a significant trust and financial loss to the government space agency due to this kind of devastating incidents. We can see that a failed space mission could result in an irreversible accident, which could lead to financial loss or even loss of life. To avoid such cases, the objective of this analysis is to analyze the factors that may affect the success rate of a space mission and how influential each identified factor is with the analysis of a multiple linear regression model. This analysis will be beneficial to all the government space agencies so that they can identify the factors that may affect the success rate of a space mission and how influenced they are. Based on it, they can minimize the likelihood of failure in space mission to avoid financial loss or even loss of life. That's all from me. I will pass you to the next person.
Hello, my name is Tang Rongbin. I will introduce the literature review related works. Hello everyone. I will conduct a thematic analysis based on literature I collected regarding space mission. Cost, access rate, and mission types have always been a hot topic of discussion. So the following 12 documents provide strong support for our data analysis. According to the above literature research, we found the hardware cost, imitation, and mission access evaluation are key link. By applying heuristic methods and uncertainty models, the budget can be optimized and the execution efficiency can be improved. In addition, research on reducing mission costs and improving quality reveals and the importance of rational allocation of resources at a time, as well as the practicality of systematical mission access prediction methods from the practical of small satellite mission to low-cost distributed space missions. The experience of maximizing scientific value under limited resources is summarized at the same time. The complexity analysis of the mission access show that fast and low-cost mission need to carefully balance performance and results event to avoid the risk and failure. The study also emphasizes the importance of innovative innovative technologies, applying sustainability and multi-objective object optimization, as well as the potential for promote multi-point sensing technology at a low cost. Together, these studies provide theoretical support and practical guidelines for the realization of economical and efficiency space missions.
Hi, my name is Snyder, and I will be presenting about the exploratory data analysis part. First of all, I'm going to talk the source of data. The data we get from Kaggle website, the dataset appears to represent simulated or hypothetical data about space mission. As you can see from the snippet of my RStudio environment, this dataset has 500 observations and also 15 variables. Some of the key variables are mission ID, mission name, launch date, target type, target name, mission course, scientific yield, and also the crew size. So now you are looking at the statistic of the data. Every variable processed here is a variable that is a numerical instances. So they can have the descriptive statistic for it. Like for example, the mean, standard deviation, mean and max. For example, the first row distance in light years, the mean for it is 25.48, standard deviation is 14.94, mean is 0.35, while the max for it is 49.90. It goes until the bottom for the other variables, so you can just look at it. For your information, in the dataset, there are no missing values at all, so yeah, that's good. These are some of the unique values in categorical variables. You can see it from the screenshot. The target type has a unique value of star, exoplanet, asteroid, moon, planet. The target name has unique value of Titan, Betelgeuse, Mars, Proxima b, Ceres, Io, Europa, and so on. Now we're gonna take a look on the visualization part. We will start by examining individual variables to understand their distribution. So the first one is distribution of mission cost. We analyze the cost distribution of mission using a histogram with a density plot. The results show that mission costs are heavily skewed with a few extremely expensive missions. Second is about the distribution of mission success rate. We examine success rates across missions. Most missions have high success rates, but a few outliers show significantly lower success rate. The third one is about crew size distribution. As you can see from here, the box plot analysis revealed that crew size vary widely, though most missions have moderate crew size. The fourth one is mission type frequency. Using a bar chart, we identify that research, research missions are the most common mission type. Now we will explore the relationship between two variables. It's about relationship between mission cost and success rate. Through a scatter plot, we observe a slight positive correlation between the higher mission cost and higher success rates. Here, it is about scientific yield versus mission duration. The scatter plots show that longer missions tend to produce higher scientific tasks. And now finally, it's about mission success by target types. Here, a bar chart revealed that certain target types, like asteroids, have higher average mission success rates. In conclusion, mission costs are skewed, success rates are generally high, crew size vary, and research is the most frequent mission type. Additionally, cost tends to correlate with success, and longer mission yield higher scientific output.
Hi, I'm Daniel, and for my part, I'm going to talk about the method used in our report. We have used two methods in our report, which is ADA and MLR. These two statistical techniques allow us to examine the relationship between a dependent variable, which is mission success rate in our report, and other several independent variables like mission cost, crew size, and mission duration. So let's move on to the first one, the exploratory data analysis EDA. So we have used EDA to do the data analysis to gain a deeper understanding of the dataset we have chosen. This involves checking the distribution of key variables like mission cost, success rate, and scientific yield. And we also visualize the relationships between the variables using bar chart and scatter plots, which has provided in the previous part of our report. And the second one will be multiple linear regression (MLR). So after we have explored the data using the EDA, we use the MLR model to quantify the impact of various factors on the mission success rate. In our model, the success rate is a dependent variable, and the other variables like mission cost, crew size, mission duration, and scientific yield is independent variables. And this is the MLR equation we have used for the mission success rate. Moving on to the next one will be the results and discussion. So we will begin with the exploratory cost distribution. The first one will be mission cost distribution. The distribution of mission cost has shown a right skew pattern, with a few missions having very high costs. This means that even though most of the missions are relatively inexpensive, but there are still some few extremely costly missions driving up the overall average cost. And the second one will be mission success rate. The mission success rate generally hover around 92.6%, with the lowest being 66% and the highest being 100%. This shows that space missions tend to have a high success rate overall, but there are some variations across different mission types and targets. This means that different mission type will affect the success rate of the space mission. And the last one will be crew size distribution. The crew size range from 1 to 99 in the space mission, with an average of about 50 crew members. This variability can reflect the difference in mission complexity and the type of mission, for example, colonization and research missions. And move on will be the multiple linear regression MLR results. The first one will be mission cost. So for the coefficient of mission cost is positive. This means that with a higher mission cost provided for the space mission, it is associated with a higher success rate. This can mean that the mission with larger budgets will have more resources allocated to planning, technology, and execution for the project, leading to higher likelihood of success. The second one will be crew size. The crew size also shows a positive relationship with success rate. This means that the missions with more personnel tend to be more successful. Larger crew size may bring greater expertise and allows for better management of mission tasks. And this means that more human resource can be used to work with the space mission. The last one will be mission duration. The mission duration was found to have a negative coefficient, meaning that the longer missions tend to have, it will have a lower success rate. This could be due to the increased complexity and potential for failure as the length of the mission increases. Lastly, we'll talk about the comparison with previous studies. The analysis in our report is consistent with other space mission studies, for example, research provided by NASA and other space agencies like SpaceX. They have also shown that with higher budget provided for the mission, it will help to increase the mission succeeding rate. Furthermore, other studies have also suggested that missions with larger crew size can also help to increase the success rate. However, on the other hand, the negative relationship between missions duration and success rate is supported by findings from earlier missions, which means that with the increasing of mission duration time, it can lead to increase the risk of technical and logistical issues. And this is all for my part.
Hello, My name is Yangzhuo Chen. The number 6 is the limitations and future study. The first is the limitations. The first one is uneven target data. The unbalanced information on stars and other targets make analyze harder. Number 2 is weak links between factors, lacks clear details on how technology or environment affects success. Number 3 is missing details. Important data like proportions, schemes, and tools are not included. Number 4 is acknowledging the outside factors. The political issues and teamwork between countries are not considered. Number 5 is not fully global. The dataset may not cover machines from all over the world. The part 2 is future studies. The first one is at more data, including the technology details and economic changes for better understandings. Number 2 is clear success rules. That is for the machines for more results. Number 3 is study costs and benefits. Use models to balance the machines' expense with benefit to securities. Number 4 is explore knowledge, and number 5 is focus on teamwork. Study how countries work together or how these affect machines. The number 7 is the conclusions. Space explorations help science and technology growth, benefiting life on Earth. Because it is complex and expensive, global teamwork is to make it better. Overall, it is a big step for ourselves, helping us explore and understanding the unknown.